So far, we've introduced the overall modeling framework that we follow in this class. In the current podcast, we start implementing this framework for modeling the first process that we analyzed in this course, water flow in soils. The modeling of water flow in soil is not an easy thing, and this because of many reasons. First, soils are very heterogeneous, which means that their properties change in space. Within a landscape, this heterogeneity may be expressed by the presence of different soil types. Each soil type may have their specific properties, which will affect the water flow process. We may easily understand, for instance, that water flow in a sandy soil type may be completely different than water flow in a clayey soil. Heterogeneity may also be expressed at smaller scales. Within a given soil unit, in a landscape, other expressions of variability may appear. And also at a smaller scale of soil profiles, the agnostic soil horizon will be expressions of spatial variability. We will come back to this variability at different spatial scales shortly. A second reason why the modeling of the soil water flow process is complicated is related to the fact that the water flow process is very dynamic, which means that the intensity of the process also changes in time. We may easily understand that water flow in soil will be affected by the weather. We know that precipitation may increase the water storage and direct the water flow downward. We also know that evapotranspiration reduces this storage and direct the water flow upward. And we also know that both precipitation and evapotranspiration are very time dynamic. A rigorous description of water flow in soil needs therefore also to consider the variability of processes at the boundary of the soil system and consider the variation of climate, soil cover, soil use, soil management as part of the system to be modeled. A third reason why the modeling of soil water flow is complicated is related to the nature of the soil itself. A soil is a porous medium, and it is composed of loosely mixture of solid, liquid, and gaseous materials. The soil pores are also not always completely filled with water. Soils can be very dry or very wet, and everything in between. In the case the soil pores are not saturated with water, specific forces will affect the mobility of water which are related to capillarity, a phenomenon that appears at the interface between liquids and air in the pores. Also, when the soil water status change, the soil hydraulic properties will change. The soil hydraulic properties are the properties that determine how much water can be retained in the soil, how strong this retention is, and how easy water will circulate through the soil. We will come back to this later in this podcast. Anyway, the fact that the soil properties, and in particular the soil hydraulic properties, change with the soil water status results in the fact that the soil water flow process becomes a strongly nonlinear process. And nonlinearity implies that the change of the input boundary condition with a given factor of a given system will not necessarily result in a similar result at the output boundary of the system. Nonlinear systems are generally more difficult to model than linear systems. We also come back to this later on. The soil water flow process is therefore complex. But the complexity of the process does not imply that we cannot model it. On the contrary, by setting different hypotheses, we can handle the process in a rigorous modeling frame. And for different hypotheses, different modeling descriptions will be obtained. In this class, we follow a rather traditional continuum approach for modeling water flow in soils. The approach considers that complex spatial, heterogeneous, and time dynamic processes can be described with rigorous physical law, first at the scale of an infinite small but representative elementary volume, and for an infinite small time increment, and then the small scale description can subsequently be integrated in space and time to obtain a description of the water flow process continuously through the complex soil domain. The approach will be based on classical soil physical principles. We do not develop in this class all soil physical concepts. We expect that the student have followed already an initiation in soil physics. In case this prerequisite is not met, we strongly suggest you to follow first a soil physical course. If you are French speaking, we can suggest you to follow the class L'eau et le sol, hydrodynamique des milieux poreux, which is available on the EDX platform. In this podcast, we will try to summarize the most essential aspects, concepts, and principles that are elaborated in detail in this EDX course. The result of this summary will be the formulation of the governing differential equations for describing water flow in soils. We start with the notion of a representative elementary volume. Soils are heterogeneous, which means that they vary in space and that we need to handle this variability if we want to model a soil process. The variability of soil properties can be expressed at different scales. At the scale of a landscape, soil heterogeneity is expressed by different soil types. At other scales, other sources of variability may be expressed. Within a given soil type, for instance, variability may appear by the appearance of different soil properties. And within the soil profile, variability can be expressed by different diagnostic horizons. And within the soil horizons, variability can be expressed by different soil aggregates. And so on, until we reach the individual level of soil particles. Hence, soil processes can be described at different hierarchical organized scale levels, and at each scale level we observe spatial variation of soil properties. In order to integrate the variability in a convenient way, we need to define an appropriate resolution for which we can define soil parameters, properties, and processes. The resolution scale that we consider in this class is a so-called macroscopic scale for which a macroscopic representative elementary volume is considered. Suppose we have a dry soil volume as depicted in this slide, corresponding to the lower spatial hierarchical level and hence the high spatial resolution. In such soil volume, we observe the distribution of soil solid particles, soil in grey, soil air in white, and other organic particles in black. Let's consider now a virtual experiment in the soil and suppose that we want to determine the porosity of the depicted soil. The porosity is, by definition, the ratio of the volume of air compared to the total volume. For evaluating this porosity, we can sample the considered soil with a given soil sampling volume. Suppose that we sample this soil with sampling volumes of different increasing sizes, V1, V2, V3, V5, and so on. If we evaluate the porosity for the different samples, we will not necessarily obtain the same results, as the number and the volume of pores and particles in the different samples will not be the same. The porosity value will therefore vary considerably for the small sampling volumes, but as the sampling volume increases, the porosity value of the soil will tend towards a constant value. If such a constant result is obtained, we have a sample size that is representative for assessing the porosity of the soil. We consider in our approach that at the local scale, such a representative elementary volume can be defined for the soil properties that are involved in the soil water flow process. We consider also that we can determine experimentally these properties at the scale of the representative elementary volume. In our approach, this corresponds to the macroscopic scale and will have a size of the order of magnitude of a typical soil sample, that means some 10 to 100 grams, or typically a soil core of 100 cubic centimeters. How does that work conceptually? Well, let's consider this hill slope soil. The hill slope soil is heterogeneous, which means that soil properties will change horizontally and vertically. Consequently, conceptually, we decompose the heterogeneous hill-sloped soil in homogeneous local scale volumes that we consider representative for the local scale macroscopic processes. At the scale of the representative elementary volume, we define properties and processes that control water flow in soil. In our conceptual model, we define these processes based on standing physical principles such as the mass conservation principle and others. So far we introduced the spatial variability of properties and how spatial variability can be conceptualized by decomposing a heterogeneous soil at local scale in local scale homogeneous units that are representative for macroscopic soil properties. A similar approach can be developed for handling the temporal variability. We introduce the instantaneous infinite small time step delta t, which is considered representative for defining the dynamic of the soil water flow process. With the consideration of the macroscopic REV, the representative elementary volume, and the representative time step, we can obtain a model that describes the change of water storage at the scale of the REV during the representative time step. This model will be formalized in the form of differential equations for which we consider that the REV is infinite small but macroscopic, and the representative time step is also infinite small but macroscopic. This allows us to define the macroscopic properties continuously in space and in time. The last step of the conceptual model will consist in the integration of the differential equation, which allows to make this macroscopic description continuously in space and time.